All right, so I wanted to take a look at trying to understand what's the meaning of a Thevenin equivalent circuit. And I guess the same is true for a Norton equivalent circuit. It's a really important analysis technique, and I know it's one that students are often pretty uncomfortable with. So I wanted to take a closer look at it. So any type of circuit element that you have, whether it's a resistor, capacitor, inductor, voltage source, current source, whatever, has what we call a VI characteristic. So this thing here I'm showing on the left, all right, so just a simple resistor, I know that V, the voltage across it, is equal to I, the current into the plus terminal, times R. I can draw that if I write V here on the y-axis and I on the x-axis. That guy's just a line, right? That looks like this, going both ways. The slope of that line is R, okay? The idea of this is what I call, like I said, a VI characteristic. And all circuits have some kind of VI characteristic, okay? For instance, if I just have a pure voltage source by itself, that pure voltage source, let's say VI, if I look at that guy, let's say this guy has, I don't know, 2 volts as his voltage. If this is V and this is I, then the voltage I always get out of this thing is going to be 2 volts. Okay? So the important thing about a VI characteristic is it tells me what voltages and currents are possible for the element that I'm looking at. So in the case of a resistor, right, for a resistor, what I see is if I know the current, if I know current, I know voltage, right? Because simply as an example, if R is equal to, let's say, 2 ohms, and let's say I is equal to 0 amps, I know automatically that V equals I times R, so 0 times 2 is 0. If I is equal to 1 amp, V is equal to 1 times 2, or 2 volts. If I is equal to 2 amps, V has to be equal to 4 volts, right? In other words, if I know the current, I automatically know the voltage when I have a resistor. So I have a well-defined IV characteristic. In the case of a pure voltage source, on the other hand, it's a little bit different. I always know the voltage across here. I always know the voltage in this case is 2 volts. But any current is possible at that 2 volts. It all depends on what the circuit is that's hooked up to it. So all things viewed from these terminals have a set of IV characteristics. All right, so even if I have a complicated network like what I'm showing up here on the right, so I'm trying to show that, let's say I've got a box, and inside that box is a bunch of voltage sources, a bunch of current sources, a bunch of resistors, could be capacitors, inductors. The idea is I should be able to figure out an IV characteristic for that circuit. In other words, from the viewpoint of these terminals A, B, I should be able to figure out if I have a particular current coming out, what voltage will I see here at these terminals? The idea of a Thevenin equivalent circuit, and really also a Norton equivalent circuit, is that if I know this IV relationship here, if I can make a simpler circuit that represents all the complicated things inside this box, if I can make that simpler circuit and make sure that that simpler circuit has the same IV characteristics at this port, then the two things are entirely equivalent to each other. That's sort of the basic idea, is if I can take a complicated circuit and make a simpler one that has the same IV characteristics, I've basically come up with a way to greatly simplify my analysis. All right, so I want to follow along with that for a second. Let's say I've got sort of what I call a non-ideal source. What I'll call a non-ideal source. All right, that non-ideal source has an open circuit voltage and some sort of resistance. Okay. Now that's ultimately the Thevenin equivalent circuit model that we make for any network. I'm going to call this just a non-ideal source for a minute. And this guy I can think of as having a VI characteristic at that terminal. Okay, so think of this guy as a battery, right? Essentially, what this could be modeling, right, is if I have a battery, right, any old battery like you would have, if I just measured the voltage across that battery, I would get a VOC, but if I started drawing some current out of that battery, then effectively the voltage would change a little bit because of some resistance inside of it. Okay, so let's see if we can understand the VI characteristics here. And let's say basically what I would do is ultimately hook up some sort of a load to this thing. All right, I'm going to show that as a variable resistor. So variable resistors we always show with a line through them like that. And let's say that RL can span a range from RL basically equal to infinity, which would be an open circuit, and then RL could decrease all the way down to 0, right? That spans all possible ranges of load resistance, infinite to 0. I can't go negative for a resistance, right? This guy would be short circuit. If I think hard about this, just from a circuit analysis perspective, in this particular case, the voltage V has to be the open circuit voltage, and the current has to be equal to 0. If I think about this case, where I have a short circuit, the voltage V, the voltage V has to be equal to 0. Fix that there. If I think about the short circuit condition, the voltage V has to be 0, right, because RL is equal to 0. So the current must simply be VOC divided by RS. So a couple of things to note. When the resistance is at its smallest, we know that I is largest. So current is at its largest. In this case, current is at its smallest. In other words, current is 0, whereas with the short circuit, the current is as large as it's ever going to be, and we call that the short circuit current. Okay. Now, what happens if the resistor is somewhere in between? Well, if the resistor is somewhere in between, I have to sort of do some KVL analysis to kind of figure out how to analyze that guy. I'm going to start to draw for myself the IV characteristic. So here's V, here's I. So when I equals 0, we know that V equals V open circuit. So I'm going to put that here. Right? This is the line, right? Basically our y-axis here. Our y-axis is the line where I equals 0. So I put VOC as the value of the voltage when the current is 0. And when the voltage is 0, I know the current is I short circuit. So I'm going to put that over here, right? Because right along the x-axis, the voltage is 0. What we're going to find is that if the resistor is somewhere in between infinite and 0, the VI characteristic lies somewhere in between those 2 points. Now, if I want to see that, I can derive my VI characteristic by just doing a KVL. Right? By KVL, I'm going to go essentially here clockwise, starting in the bottom, like I always do, the bottom left. So 0 equals minus VOC. 0, so KVL, 0 equals minus VOC plus I times RS equals, plus V. Okay, so what have I done? I said I go from minus to plus across VOC. I go plus to minus across RS, and then I go plus to minus across V. Now I could have plugged in that V was equal to I times RL, but I didn't want to, and I don't have to. Okay, if I rewrite this guy, I can rewrite this and say V equals VOC minus I times RS. Right, so in some sense, this is basically like an equation of line where I say y equals mx plus b, and we called b our y-intercept, right? And we called m our slope. Effectively, I've got the same sort of thing here, where v is my y value and I is my x value. So that means basically that m, my slope, is equal to minus rs. All right. So in other words, I have a line that's decreasing as current goes up, and the slope of that line is rs. And I have a y-intercept of V open circuit. All right. So I can see that this line, a couple of things that's important about this line. So if V equals VOC minus I times RS, a couple of things I can see. Well, when I equals 0, V equals VOC. Okay, just like our circuit analysis led us to believe previously. Now I look at this guy and I say, well, what happens if V equals 0? In other words, I put a short circuit across this thing. If that's the case, I get that 0 equals VOC minus I times RS, where that I must end up being VOC divided by RS. Notice that this is the same thing we defined as the short circuit current above. So what I know now is that this VI characteristic is a line that starts at the y-intercept and decreases to the short circuit current like that. And the only set of possible voltages and currents, no matter what resistance I put onto this thing, the only possible set of voltages and currents that can come out of this network are on this line, right? So up here I have RL equal to infinity. Here I have RL equal to 0. And anywhere on this line is basically for an RL anywhere in between those two extremes, okay, is where I fall. Essentially, it gives me the range of possible voltages and currents I can see at the output terminals of this particular circuit, all right? So a pretty straightforward idea, but if I just look at this and I say, this is an example, let's say I have 1 volt and I have 2 ohms here, okay? Here's V, here's I, like that. Pretty straightforward type of circuit, okay? One thing I can immediately see is that if RL is infinite, so in other words open circuit, for this particular guy, it must be the case that V equals 1 volt, right? Similarly, if RL is equal to 0, RL is equal to 0, the circuit just simply is 1 volt, 2 ohms. And so V, in this case, V equals 0, and I equals essentially just the open circuit voltage divided by the internal resistance. So 1 volt divided by 2 ohms, or half an amp. So this is the highest possible current. This is our short circuit current, okay? So if I start to draw that IV characteristic, here's I, here's V. I say, all right, I start out at 1 volt here and 0.5 amps right there. And I can derive the IV characteristic just like I did previously by KVL, right? By KVL, 0 equals minus 1 volt plus I times 2 plus V. All right, so again, starting here and going around counterclockwise, I get that relationship by KVL. So V equals 1 minus 2I. All right. If I were to plot that thing over here, right, if I were to plot this guy, I see I have a y-intercept of 1 and I have a slope of negative 2. So if I have a slope of negative 2, that line is going to end up looking like this. Okay. So I see that just as before, all right, just as I sort of predicted, the IV characteristic for this particular circuit is a line that starts out at the open circuit voltage and ends at the short circuit current. So this is my VI or IV characteristic. Okay, so it tells me all the possible voltages and currents for that circuit. So let's just say, for instance, that, I don't know, let's say that I put an RL onto this circuit of 1 ohm. Okay, and here's 1 volt, 2 ohms, and then 1 ohm here, and this is my RL, and I call this voltage here V, okay, and call this current I. All right, so simply put, if I look at this guy, I can see that I'll start with the current. I has to be 1 volt divided by a total of 3 ohms, or 1/3 of an amp. So then by KVL, V has to be equal to 1/3 of an amp times my 1 ohm load, or 1/3 of a volt. Okay. Now that must sit on this IV characteristic that we drew above. Okay. And the way we can see that is I can remember that my IV characteristic is V equal to 1 minus 2I. So if I plug in V of 1/3 of an amp, right, because remember this guy is V as a function of I say that that's 1 minus 2 times 1/3, or 1/3 volts. Okay, so essentially what I'm saying is I've got a point here on this line, so this point being 1/3, 1/3, which is true when my resistance on this guy is apparently 1 ohm. Okay, so the basic idea is just that this IV characteristic, right, basically tells me all the possible voltages and currents that I can ever see at the terminals of that circuit. All right. Now the Thevenin equivalent idea basically takes and makes use of that idea. All right, so I'm going to move this over here, and I'm going to take a look at a network. All right, so let's say what I have is some sort of a circuit, and I've drawn this in Simulink, which is a simulation tool, and I don't know what's inside that circuit, right? What I have is a particular voltage of the terminals and a particular current coming out. And what I'm ultimately going to do is hook up an RL to this guy, a load resistance, and I'm going to change that load resistance. Okay? So here, I don't know what's in this box. I have absolutely no idea what's in this box. What I've done is I've hooked up a current sensor. So the current sensor measures the current coming out. I can put a load right here, okay? And then right here is a voltage sensor that I've placed across where the load resistor will go to tell us what the output voltage is going to be. So basically what I want to do is I want to change that load resistor to measure essentially what the VI characteristic looks like coming out of this box. Then I'm going to open up the box and I'm going to try to make a Thevenin equivalent circuit and see that the IV characteristics of those two things match. Okay, so let me first do this. Simplest things to do is let's try to do this with first RL at infinity. So essentially our open circuit condition. All right, that's what I've got shown here. Let me run that simulation. So a couple of things to note. What I have here out of my current sensor is I have a current display and a voltage display. So what I can see is the voltage apparently is, in this condition, the voltage is equal to 5 volts and the current is equal to 0 amps. Okay, we would expect that the current should be 0 amps. So at this point I know that the open circuit voltage is apparently 5 volts. So now let's do RL equal to 0, our short circuit condition. Okay. So in our short circuit condition, I can take these two leads and touch them together. All right, now the voltage has to be 0 because I basically put a wire there. So now I run this guy. All right, now the voltage is 0, just like we expected. So V equals 0 volts. I, on the other hand, is equal to 0.5 amps. Now, I'm going to try a bunch of other resistances. So I said basically this is my two boundaries, right? This is the maximum current. This is our I short circuit current. This is the maximum current I can ever get out. And then up here I had the minimum current I can ever get out. Now I want to try all the resistances in between, okay? To try to trace out, basically my goal is to try to trace out the IV characteristic of this thing. So I'm going to try RL equal to 30 ohms. RL equal to 20 ohms, RL equal to 10 ohms, RL equal to 5 ohms, and then RL equal to 2 ohms. Okay? Bunch of different resistance values. So let's try that. So I'm going to delete my short circuit there. And this tool I use called Simulink has the ability for me to place a resistor. So I go in here and I find a resistor, bring it over, okay, I'm going to rotate this guy clockwise, okay, and place this across the circuit like that. And let's put the value that I want. So it starts out at a value of 1 ohms, but I said I wanted to start at 30. So 30 ohms. All right, now I run that. Now in this case, at 30 ohms, I can see that I get V equal to 3.75 volts. So a little less than the maximum. And then a little bit more than the minimum current, 0.125 amps. Now I change this guy to 20 ohms. Run it again. Okay, and I get V equal to 3.333 volts, and I equal to 0.1667 amps. Okay. Then I change this to 10 ohms. Run it again. And now I get my V equal to 2.5 volts. My I equal to 0.25 amps. Keep going with it. I know this is tedious, but just keep going with it. Let's change my RL to 5 ohms. Okay. So at 5 ohms, I get my V equal to 1.667 volts, and my I equal to 0.3333 amps. And now I try this guy at 2 ohms. Run it one more time. So at 2 ohms, I get a V equal to 0.8333 volts and an I equal to 0.4167 amps. Okay. Now, what I did is I want to visualize those guys. And so I created separately a simple little MATLAB script where I wrote those numbers down. So let's see what I did. So basically I created two vectors here, IT and VT. And those are basically the values that I'm looking at right here. So let's see. I said that when I have 0 volts, I have 0.5 amps. So the way I wrote this is, all right, I'll start with this. When I had 5 volts, I had 0 amps. So 5 volts in the VT vector, 0 amps in the 0 vector, in the current vector. So 5 volts in the VT vector, 0 amps in the IT vector. Then I say, okay, well, when I had 0 volts, I had 0.5 amps. So I say 0 in the VT vector, 0.5 in the IT vector, and then I kept with it. And I said, okay, when I get 3.75 volts, I get 1.125 amps. So here you can see 3.75 volts in the VT vector, 0.125 amps in the IT vector. And then I did it for this condition, this condition, this condition, and this condition. Put them all in these vectors, and you can pause the video or whatever and take a look to see that they actually match. And then what I'm going to do is I'm going to plot IT and VT together, and I'm putting a little asterisk where each one of those points is. So I run that, and there's my graph. I can see, okay, it looks like there's probably a line that joins all these asterisks, right? So here at my short circuit current, 0.5 amps, I have 0 volts. And here, right, where I have 0 amps, I have 5 volts. And each of these points here corresponds to the load resistances that we just tried, okay? Now, what I want to do is this, so the line basically that would connect all these points would be the IV characteristic for whatever's inside this box. Now, what I want to do is try our Thevenin equivalent idea and try to make a Thevenin equivalent for what's inside that box. It should completely match up with what we just did. So in this case, all right, I'm going to have to open up my box. All right, and there we have it. That's what's inside my box. So let me draw that out here. So apparently what I have is a voltage source, a resistor, and then another resistor connected to the terminals. So these guys right here, these two terminals, were what we had previously connected to the outside world with. In other words, we put RL across these two terminals. All right, now let's get some values here. So this guy is a 10-volt source. So this guy is a 10-volt source. This guy is a 10-ohm resistance. This guy is a 10-ohm resistance. And this guy is a 5-ohm resistance. Like that. All right. So now what I want to do is I want to make my Thevenin equivalent circuit looking into this thing. All right. So step one of my Thevenin equivalent circuit, I say, okay, well, here's V, here's I. At those terminals, let's call them A, B. I want to say, what's the open circuit voltage? What is VOC at terminals A, B? Well, if there's open circuit voltage conditions, then basically this current here equals 0. So all of the current from that 10-volt source must flow through these two 10-ohm resistors. All right, if that's the case, I'm only measuring the voltage across this 10-ohm resistor. So if that's the case, I basically have a voltage divider. So I know that VOC, which is V I'll write it this way, with I equal to 0, that has to be basically 10 volts divided by 10 ohms over 10 ohms plus 10 ohms. All right, do your math on that, and it quickly works out to be 5 volts. Okay, so then I see that my VOC has to be 5 volts. Now I need to find the R Thevenin. So what is R Thevenin at terminals A, B? So this basically says, all right, what resistance does this current here flow through? So in that case, I need to shut off the 10-volt source. and I see that I have 10 ohms, 10 ohms, 10 volt source is shut off, and then I have 5 ohms. All right. So in other words, what resistance does this current I flow through? Well, it clearly flows through this 5 ohm resistor, but then it flows through a split between these two 10 ohms. And if I look at this in these conditions, basically, right, if this is V1 and this is V2, just by straight KVL, V1 equals V2, so I can see those two 10 ohm resistors are in parallel. So I put the two 10 ohms in parallel, 10 ohms in parallel with 10 ohms. If you sit back and you do that math, you'll see that that's 5 ohms. So I can simplify this circuit to this, like that. And then I have a current I flowing out. So pretty clearly here, it looks like the total resistance that I see is the series combination of the 5 and 5. So 5 ohms plus 5 ohms equal to 10 ohms is the total resistance. So what I've said is that for this particular circuit, I have VOC equal to 5 volts, and I have R Thevenin equal to 10 ohms. Okay. All right. Now, what we did previously, right? What we had done previously when we analyzed this thing, is I said, well, I can think of that thing as a black box. Now I'm going to say replace that black box with this guy here. And I'm going to say, well, so now let's put the RL onto this circuit instead of onto the black box. And if I want to analyze this thing, I could do it for a bunch of different resistances, right? Or I can just basically say, okay, well, let's label that guy by KVL. Again, starting in the bottom left and going around clockwise, I could say 0 equals minus 5 volts plus I times R Thevenin plus V. Okay, so that means that V equals 5 minus I times R Thevenin. And let's plug in, that's 5 minus I times 10. Okay. Now, what I want to do is I want to draw that IV characteristic here. Okay. So I go to my MATLAB. All right. And in my MATLAB here, what I've written is, okay, so this equation here, V equals 5 minus I times 10. Okay, I've written that here on line 5. V equals 5 minus I times 10. And I've defined I to be a vector of currents that starts at 0 and goes all the way to 0.5 in steps of 1 milliamp. Right? Why am I starting at 0? Well, because that's the smallest current I can ever have at open circuit. And why do I go to 0.5? Because I know that in this particular circuit, if RL is equal to 0 ohms, that I must be equal to VOC divided by RTH. We call this the I short circuit current. For this particular circuit, it's 5 divided by 10, or 0.5 amps. Okay. And then what I'm going to do is, you see up on top, is I've written all the same values that I got in my previous analysis with the simulation, right? So with 0 amps, 5 volts, 0.5 amps, 0 volts, 0.125 amps, 3.75 volts, all that mundane stuff. So I'm going to say plot IT and VT together with those asterisks again. But now I want to plot versus I want to plot that voltage characteristic. So if I run that guy, now I can see those blue asterisks that I got when I ran the simulation at different RL values. And that red line is basically the IV characteristic of my Thevenin equivalent circuit. So the idea here is that what I've just shown is if I take this circuit right here, where I just say, okay, I don't know what's inside this box, and I just start hooking resistors up to that circuit, what I can see is that the IV characteristic given by these blue asterisks is exactly the same as the IV characteristics of the Thevenin equivalent circuit that I found over here. So given that this simplified circuit has exactly the same IV characteristics as the original complicated circuit, what that means is I can replace the complicated circuit by this simplified circuit. And that is the whole power of the idea of Thevenin equivalence, is to say that I found a way to come up with a simpler circuit that's entirely equivalent to the original one. All right? And the reason it's equivalent is because the IV characteristics at these terminals here are exactly the same. Right? In other words, the relationship between the current coming out of these terminals and the voltage across these terminals is the same both for the original complicated circuit inside this box and the simplified circuit shown over here. That's really sort of the big idea. Now, one important thing, I guess, that I'll say, right, is if you look at these IV characteristics, so here's I, here's V. So it looks like that, let's say. So this point right here is, we said the I short circuit current, 0 volts. And this one is 0 amps and V open circuit. So the other thing is I said, well, the slope of this line is minus RTH. So one important thing I can see about this circuit is the fact that the slope of that line, right, slope is always equal to rise over run. So in this particular case, the rise is negative VOC. So in other words, as I go from here to here, I go down a negative VOC, and my current goes from 0 to I short circuit. All right? The slope of that line is clearly negative RTH. So one thing that we do, right, when we have complicated circuits that have all sorts of, dependent sources and things like that, we'll say, well, if I want to know that R Thevenin is simply equal to VOC divided by I short circuit. In other words, I can figure out what that Thevenin equivalent resistance is by knowing VOC and ISC, because essentially the fact that the IV characteristic, the slope of that IV characteristic, is the Thevenin equivalent resistance, and it also happens to be equal to VOC divided by I short circuit. And that's why that trick tends to work. All right, but the important takeaway here is that I can take any sort of complicated circuit, any complicated network with a bunch of sources and a bunch of resistances and all that kind of stuff, and as long as the circuit I replace it with has the same IV characteristics at its terminals as the original circuit, then the two circuits are entirely equivalent to each other. That's sort of the big idea. All right, and that's what really allows us to make a lot of simplifications. All right, so hopefully that helps a little bit to understand how those things kind of operate.